Welcome, everyone, to the SAMPI Thermoplastics Technical Committee meeting. We normally have these on a monthly basis, but this month we have kind of special guest on Offringa, so we're having a slightly different format to our usual sort of more business-oriented meeting. We're certainly quite a large and international group. I'm David Leach with ATC Manufacturing, and I'm the co-chair of the SAMPI Thermoplastics Committee. You'll also see Julieta Barreta-Robles, who is co-chair with me as well. Julieta is at the National Research Council of Canada in Montreal. And our group secretary is Alberto Lario Cabello, who is with Torre in the Netherlands. And that kind of reflects kind of some of the diversity of the group as well. Just to talk about some of the activities we have going on, because those of you who are all SAMPI members should have seen the latest edition of SAMPI Journal, the September-October edition that just came out. Thermoplastic composite technologies. So we were involved in identifying and kind of collating the papers for that edition. We will be making a presentation at the SAMPI Europe conference. That'll be related to the state of technology activities. Of course, we authored the section in the SAMPI State of Technology Industry report on thermoplastics and gave a presentation on that at the SAMPI conference in Seattle in the spring. And so at the SAMPI Europe conference in Madrid in a couple of weeks' time, myself, Cedric Dupin from Dayer, and Alberto from Torre will be giving an overview of that as well. Just a reminder that the call for abstracts is out for the SAMPI conference next year. That's the spring conference, which is in Long Beach in May. There will be thermoplastic sessions at that again. The last year or so, that thermoplastics has been sort of rolled in under advanced material advances. But next year, we will have dedicated thermoplastic sessions. So anyone who's interested, please submit your abstract. Those are due the 1st of October. You can go on the SAMPI website, and it's a pretty simple process submitting an abstract. We're also working on the State of Technology Industry Report update. SAMPI leadership has encouraged us to kind of review that and add to it. So we're working on additions to that. And we've also been making some short videos, which SAMPI will be releasing, talking about some of the different sections, because we broke our technology industry report down into 6 sections overall, with separate leaders collating information for each of those. So there'll be short videos on those coming up. And then just recently, we've initiated a literature club, which is being led by Lena Ganbury at Mississippi State University. And Lena on the line?
She is. I'm going to promote her so she can give
can we unmute Lena for a moment here so that you can
Hi, Lena.
You can just give us an update on that as well.
Yes, we can hear you.
Okay, great. So thank you for the shout out to David. So this is a club that we're kind of just starting as a breakout group. You can see the flyer on the bottom right hand side of your screen. The purpose of the group is really just for those of the people who are interested in becoming familiar with, or staying up to date with the current state of the art. And we will have our first meeting on September 27th. The tentative time for that is 1:30 p.m. Central Standard Time. So I'll be kind of talking a little bit more about the purpose of the group at that meeting. So if you're interested, please feel free to reach out to me. You can do that on SAMPI 365 or via email. Thank you.
Great, thanks, Lena. So kind of all of this reflects there's obviously a lot of interest, a lot going on in thermoplastics, and SAMPI Thermoplastics Technical Committee is very active in all of these areas. Over the summer, we have been hosting a number of kind of guest presentations from experts in particular field. So today we are very honored, I would say, to have Arnt Offringa from GKN Fokker. Arnt is director of the technical center, GKN's technical center in the Netherlands, and of course a SAMPI fellow as well. Arnt is going to talk on the sort of ever-increasing size of out-of-autoclave thermoplastic structures, and certainly his work on that at GKN Fokker has followed a very distinguished pattern over the years of larger and larger structures. Just a reminder that this presentation is being recorded today, so that everybody's aware of that, and also it will be available at a later date through the SAMPI website. Arnt is going to give the presentation. If you have questions, then please put them in the Q&A. You'll see down below there's both a Q&A and a chat. Please put them in the Q&A. We'll host the questions at the end of Arnt's presentation. So Arnt, over to you.
Yeah, thank you very much, David. Can you hear me?
Yep, hearing you fine.
Okay, thank you. So I will share my screen. There we go. All right, so good afternoon, and thank you for attending. It's an honor to be asked to present. So thank you, David, Julieta. I'd like to start my presentation with a bit of a short introduction on the aerospace market, and I guess why the fit is so strong with thermoplastics, also with new entrants such as advanced air mobility, and then go on with let's say, our legacy, the GKN Fokker's legacy, where we come from starting in the early 90s and progressing into current developments, where we started with very small parts and then progressed into a larger ambition to much larger parts. Today we use the autoclave in production for large components, but there is a clear need for going out of autoclave, and there's also possibilities to do so. It's my pleasure to share some ideas on this with you today. So
can I just jump in for a minute? I know
Sure,
my screen is saying you've started sharing the screen, but I'm not actually seeing anything yet.
I cannot also see it as well. It's showing as if it's preparing to share. Okay, it had shared already now. So now you're sharing.
Let me try this again. Because it did work just now.
Okay,
so
now we're seeing your screen. It's just we don't see the presentation yet.
Okay. It's not there yet.
So you just need to, because we see the Zoom screen right now.
Yeah.
On your screen.
Okay.
Yeah, it's always a challenge getting the right screen to share on the.
Yeah, because we did practice before, and all was fine.
Perfect. We see your slide now. Your first slide is there.
Phew, lucky us. All right, so right away, can you see the second slide now?
Yes, all good.
Yeah.
Okay, thank you. So to start with the market, the aerospace OEMs, the large, let's say the prime manufacturers, they need reduced weight now more than ever, not just for performance and cost, but also for emission reductions. And we see the move to non-fossil fuels as a clear sign. Think of electric flight, but also hydrogen. There is still the need to reduce costs, as always, and then the materials and processes we use clearly have to be green, have to be sustainable, and we'll get back to that in a moment. There are initiatives in the world on hydrogen. In the Netherlands, there is sorry, it's going too fast. There is a project to work on a double-walled composite tank, looking at thermosets, thermoplastics, looking at permeability, assembly technologies. This is led by Torre, and it's a fantastic new environment to be active in. Liquid hydrogen will be used for aircraft, so this is extremely low temperature and a huge challenge with respect to permeability and properties. But this is just starting. Another market segment which is fairly new, fairly recent, is the urban and mobility market, with the manufacturers claiming that the production volumes will be quite large, at 5,000 plus, maybe 10,000 vehicles a year by 2035 or maybe even earlier. However, it's different from commercial aviation. The aircraft are smaller and they fly shorter distances. And the drivers for technology are the fact that they are battery powered, so weight is of the essence, and the high rate production mandates production processes with very short cycle times. So all of these requirements add up, basically giving the need for innovative designs with lightweight and tough materials, very fast processing, and preferably low energy use during production. And for large parts, if we look at autoclaves, which is the standard today, energy consumption is fairly large. So thermoplastics fit into this picture, with materials being very tough, the polymers, there being the opportunity to create very innovative design concepts and to have cycle times which can be extremely short. Like for ultrasonic welding, for example, it's less than a second, to name an example. And then recyclability, with thermoplastics, we have full recyclability of the polymer and the fibers. So our legacy within the company from the Fokker days in the Netherlands, starting in the 1990s with stamp form parts like ribs, and then moving on to floor panels and other parts, ever larger parts. Today, our ambition is to really look at a large scale on the opportunities for thermoplastics. For example, the fuselage of aircraft, full tails of aircraft, and also at high rate. Now, this is very challenging, but how did this all start? And this started many, many years ago in the early 90s. And there was a supplier with a vision. At the time, it was Tenkate Composites, now part of the Toray Group, Toray Advanced Composites. And this picture here is of the manufacturing facility for laminates of 4 times 12 feet, 1.2 times 3.6 meters. And we see several presses working in parallel to create laminates. And with these laminates, you can, for example, create stamp-formed parts like ribs. And in the early days, that's what we did in the 1990s. So I started deep drawing and stamp forming for all sorts of aircraft. Also developing panels for wings with a creep forming process. So not an autoclave process, but creep forming. On the right is a plate which is formed by folding and by ultrasonic welding. So these are all out-of-autoclave processes. So here we are working out of autoclave up to, let's say, about 2 meters dimensions, 3 meters dimensions. Also here, floor panels for aircraft. These floor panels are sandwich structures with a core material in the middle. And to create the sandwich structures with high quality, the autoclave was used as a standard. You could possibly use a press as well for certain parts. But this was the first use of an autoclave for thermoplastics in the mid-1990s. Then along came a very important opportunity with Airbus in the United Kingdom on the A340 long-range aircraft. The wing leading edge, the fixed leading edge, was a aluminum design. And the design team wanted to investigate whether weight could be reduced by going to composites, preferably going to thermoplastics because of the possibility to weld structures together. And that's what happened in the end. So collaboration between Toray, ourselves, and Airbus resulted in this product, which is a welded structure with stamp-formed ribs, stamp-formed stringers, so stiffening elements. However, the skins themselves had to be autoclaved. We were hoping to make them out of autoclave with purely vacuum in an oven. But because of all the thickness variation in the product, the complexity of the layup, that proved to be a big challenge. So we did go to an autoclave. And here we see the A380, which also has this same product at a much larger scale. products have a length of approximately 3.5 meters and a height of about 1 meter. The welding is highly automated, so that's resistance welding. But the skins are autoclave, so fairly traditional. We see here the layup process, laser-assisted projection, then it's vacuum bagged and then autoclaved in a fairly efficient autoclave cycle. It's faster than with thermosets, but still it is time intensive, very energy intensive, and you have bagging materials which you cannot reuse afterwards. This was in the late 90s. In the early 2000s, opportunities opened for control surfaces of business jets, such as this Gulfstream aircraft. So the technology was developed in the Netherlands in a consortium, and then basically shown to several customers. And with Gulfstream, we got an agreement to implement this new technology, thermoplastics, on rudders and elevators of their aircraft. And here is the part. So, and the business case is to weld instead of to bolt, so to reduce cost and to reduce weight. 20% cost reduction mainly because of the fact that we are welding instead of riveting. And if we look at a weld under the microscope, it looks like this. And if you cover two sides, it's very difficult to see where the division is between the skin and the rib flange in this case. So today we are very proud to manufacture these products for several customers in a highly automated environment. The welding itself is on license from KVE Composites Group, which we industrialized in our company ourselves. Now, the parts to make these rudders and elevators are several. So first of all, ribs, which are up to maybe 1 meter in length. These are made in a press, so out of autoclave. But the skins, they are about 6 meters in length, and they can be up to 1 meter wide. So we don't have a good technology today to make these efficiently out of autoclave. There's a lot of thickness variation in the skin, so we do these in an autoclave. To make the skins is fairly simple. To make the spars, that's on the right bottom picture, that is a bit more complex because it requires much more attention to the bagging procedure. The spars have a small radius where the material goes at 90 degrees around the corner. So there you have to put a lot of attention into the bagging technique, and it would be very nice if we could have an alternative for this. So today we see a move in technology from what we know from several years ago, hand layup, working with fabrics, to more automated processing with unidirectional tape, where the fibers run only in one direction, and also developing new innovative concepts. For example, the picture at the right at the bottom, which is a perpendicular joint in composites, thermoplastic composites, where the polymer itself is basically connecting the two elements instead of the fibers going around the corner in a radius. To make parts with this unidirectional tape, we're looking towards more automated layer processes such as tape laying and fiber placement. And fiber placement, for example, with laser or with ultrasonic tacking, to have fiber steering and to make highly complex geometries. The picture on the right is a floor beam of 4 meters, which was used in the stunning multifunctional fuselage demonstrator, a Clean Sky 2 European project with Airbus in the lead. We also had a project called TAPAS in the Netherlands with a consortium to develop, among others, a 12-meter span skin for a tail of a business jet, also using fiber placement and the new technology to create perpendicular joints, and basically tested this technology at a full-scale test with the Dutch Aerospace Laboratory, the NLR, and achieved very good results and a TRL 6 assessment. So, summarizing, where are we with composites today on aircraft, such as narrow-body airliners? I think it's fair to say that for the vertical and horizontal tails of aircraft, carbon fiber reinforced composites are here to stay. That's the standard and established accepted solution. For the wing, it seems to be the same situation where composites offer you very good fatigue resistance and weight reduction, so less maintenance costs, so also a very good solution. For the fuselage, it's more of a debate. So there are aircraft, 787, A350, with full composite fuselages, but it has proven quite a challenge to make them weight and cost effective. And the reason is that a fuselage of an aircraft is a very thin pressurized shell, which is very damage prone, either by lightning strike or hail impact, bird impact, or even accidental impacts on the ground. So we need tough, lightweight materials and robust designs. So that might be a particular opportunity for thermoplastics in this arena. Here is a picture of the current fuselage on the Airbus A350 in Augsburg in southern Germany. It's a lightweight composite design, but if you look at the assembly process, it is quite labor intensive. And note the amount of bolts needed to attach the frames to the skin itself. So that is definitely a cost driving element. The skins are autoclaved today, and also that is something which would be elegant to move away from. So we have several projects in Europe in the multifunctional fuselage demonstrator project, Clean Sky. In the Netherlands, the focus has been on the lower half, which there's a picture on the right. So it's a collaboration between the TU Delft, including SumXL, ourselves, so GKN Fokker, Deal, and the NLR, with Toray materials to basically create a full half barrel, including floor beams, cargo area, electric systems, everything integrated, and as much as possible a dustless assembly. So welded as much as possible, and it is welded indeed. So for example, the frame sub-assemblies are welded robotically, and we see this in our tech center with the conduction welding technology. It's much like an automotive setup. Then the stringers on the skin are also welded. The Omega stringers are welded with the same process. The injection molding brackets are ultrasonically welded by SumXL, or were ultrasonically welded by SumXL in Delft to create the full fuselage. An alternative concept for fuselage is to use this new joint technology to create a stiffening in two directions, so-called orthogrid stiffening. That's also possible. Today, this is done in an autoclave. So also here we would like to go out of autoclave for these panels. And fuselage panels can be fairly large. The diameter of a small size Boeing or Airbus is around 4 meters. The length could be anywhere between 8 to 12 meters in length. So these are pretty huge panels to make. The fuselage concept is also being developed together with Gulfstream to see where it would fit on a Gulfstream type aircraft. And that's making panels with much more complex curvature. So in 2023, we are scaling up to a large length panel with this technology. So what is the state of the art? For large parts, really large parts with good quality, mostly we have to go into an autoclave. And the cycle times are shorter than for thermosets, but we do have a huge mass of steel and tooling to heat up each time. This autoclave here, which is a 3.5 meter diameter, is about 4.5 megawatts. So that's a fairly powerful autoclave. And we have a lot of bagging to do each time we bag our products with flexible foils that most often we cannot reuse. So the question is, can we find an alternative to this? And we have decided to focus on the layup and consolidation process, and also for more complex parts, the layup and co-consolidation process to make more complex products. So in this overview of production technologies for thermoplastics, the focus is here to go out of autoclave if possible. And in GKN Aerospace's Tech Center in the Netherlands, we've been blessed with the funding to invest in new equipment. So that's shown here in this overview, basically starting with the material and then laminating on a flat plane, or making fiber placed three-dimensional shapes, and then moving on to a consolidation or co-consolidation step to get the final part quality. And the product could be anything, could be a spar, could be a rib, could be a panel itself. On this picture is the result of a couple of years' work with this technology effort. Spars, so C-shaped spars on the left for Leonardo in Italy. Leonardo has a new tilt rotor concept aircraft they are going to be flying. And the question was, can we create a thermoplastic spar, or two spars actually, left and right in the tail, but then do it without an autoclave. So the spars had to be high quality with tapered thickness, large size, this is 3.5 meters, and then out of autoclave. And the same question was on a project with Airbus on the Wing of Tomorrow to create a rib for a wing in thermoplastics with complex geometry without the use of an autoclave on the right. So that's also made in the same process. And the process starts typically with a flat material. So on the left is the way we would do it several years ago, but on the right is using equipment, a machine, to lay down thermoplastic tape. It's 2 inches in width, or 50 millimeters, and it can be laid down at very high speed, up to 2 meters per second, and cut at an angle. So, and it uses ultrasonic energy to attach the layers to each other to make a laminate. And then the next step is to take this laminate into a press. It's a fairly simple press, pneumatic press with an oven behind it. So the material is clamped, as on the picture, then moved into the oven and then back into the press and quickly stamp formed into a shape, such as a spar. And this picture shows the spar, but a subscale component which was developed in the beginning. The picture on the left shows a tool to basically compress the spar for the final part quality, so-called co-consolidation tool. So we have several steps, subsequent steps, each one with a short cycle time. And we use pressure in 2 directions to create the final quality of the part. And this slide shows a large press frame of 6 meters, which fits a tool. So the tool fits inside the frame, and the tool has its own pressure system, heating and cooling. So suited for large volume production. So the flight-worthy spars are now ready, have been assembled into the tails of this aircraft, tilt rotor aircraft, and will be flying, I think, by the end of this year, or was it early next year? And the reason to, once again, to go out of autoclave is summarized in this graph, in the sense that we do have to go to very high temperature, between, let's say, 320 and 400 Celsius. But we can do this, the green line is the new process with a much shorter cycle time. And our calculations show that we should be able to save around 80% of process time and about 80% of the energy which we would otherwise need in the autoclave process. So now a new development is on urban air mobility, recently announced this summer at the Paris Air Show, is for Joby. With Joby, we have an agreement to develop and produce the control surfaces on this aircraft, which is their aircraft, in thermoplastic composites. And the positive element to add to this is not only will it be a thermoplastic component with several innovations incorporated in series production, but it will be produced out of autoclave. So in the schematics that I showed in the previous slides, that basic technology will be used to create these control surfaces. And there are 10 of them on the wing and on the tail. So the ailerons and the so-called ruddervators are all thermoplastic. And this slide shows our president and the CEO of Joby, Joben Bevert, proudly showing a prototype of the control surface. So it's 2 components that are connected to make a lightweight product. Current activities to go out of autoclave. So on the left is the forming and the consolidation process I described. At the same time, there's some very good work going on with Simpelkamp in Germany, and this together with Airbus, this has been published recently in Composites World. And the picture, the schematic at the right bottom, shows the principle of a press with which a complete half fuselage barrel could be formed under high pressure. So this would be a skin with integrated stiffening, so that the only thing you have to do is to weld on the frames to this product. The investments here are significant, so that is of course a fact. However, you make your business case, and for example, for a Boeing or Airbus type aircraft, if you have a large production volume, this does warrant a significant investment in equipment if the build rate is elevated as it is today. So how does thermoplastics contribute to sustainability, also with out-of-autoclaving? Of course, the lightweighting of materials to reduce energy use, less energy used during the production process. The third bullet is we will have less disposables during the production process, and we want full recyclability of the materials and products, resulting in less waste. So these today are drivers for technology development. And basically, to conclude on the outlook for large structures, so there is a definite need and a business case for large thermoplastic composite parts such as panel spars, beams, ribs, and assemblies. And in order to be cost effective with high rate production for the markets, several markets, we need out-of-autoclave processing. And I think the journey has really started, but it will be a focus for several years to come. So with that, I'd like to thank you very much for your attention, and open the floor if there's any questions to be asked. Thank you.
All right,
Thank
great.
you very much.
Yeah, thanks so much, Arnt, for a great presentation. I think, Julieta, are you going to kind of organize the questions here?
Yes, I will organize the questions. So please feel free, as David said at the beginning, to place your questions in the Q&A. And if you feel more comfortable also in the chat, or if you want to raise your hand, I will try to address them equally distributed. So now we already have 2 questions in the Q&A. The first one is from Moritz Grabner. Rib joints in the fuselage area were used because of the dynamic loading of the joints. How can the rigid welded joints of the thermoplastic components withstand these dynamic loads?
Okay, I don't fully understand what a rib joint is in a fuselage area, but what I could say, at least, maybe there could be another question, but is that the structural concepts I showed for fuselage have been extensively tested, both static and in fatigue. So we have to meet all the requirements that exist for fuselage type structures, and so it's critical that you get the right design to basically carry all these loads, including elements like crack stoppers, fatigue resistant joining techniques. So maybe, if the question could be clarified, we could go a bit deeper. Yeah.
So I can, if you want, I can quickly bring you in. So I have just made you panelist. If you want to elaborate, Moritz.
Yes, thank you. Thank you for taking my question. No, what I was asking for is that the dynamic loads in the fuselage, because of the pressure building up in the fuselage, is expanding those joints inwards and outwards. And if you could maybe explain more how those welded joints can take on those dynamic loads in terms of expanding and restricting during landing and flight. Thank you.
Yeah. Okay. So it depends on the concept you choose. For example, there is a concept where you have stiffeners that are integrated with the skin, so they're co-consolidated with the skin, and then the frame is welded onto the stiffening element. The frame is a circular member. Then the loading of the weld is a lap shear joint. So it's like this, right? It's in shear. So that's a fairly benign loading for a welded joint. And then the perpendicular joints between the skin and the stringer have to be of good quality to withstand the loads when you pressurize, and of course all the other loads that happen but that's a matter of making your stress calculations and seeing how evenly distributed these loads are. So the trick is to connect the frame to the skin over a large portion of the frame contour. So to not have very big steps between the welds. I don't know if it's clear.
Thank you so much. Thank you.
Yeah, thank you. Yeah.
Okay, so second question from Lina. What is the time difference for a typical thermoplastic composite autoclave consolidation versus press consolidation?
Yeah, so thermoplastic autoclave would be like maybe 6 hours. It's shorter than thermosets, but still around 5-6 hours. And press consolidation just depends on how much energy you want to push into your product to heat it up quickly. So it can be 30 minutes, can be 45 minutes, can be, so it just depends on the amount of power you put in, and the amount of power is determined by the generator you have. So a very fast process requires more investment than a bit longer process. And I guess that's a business case calculation you make. So how many products do I have to make per hour or per day? That warrants a certain investment, but it can be fairly quick. And if it's an isothermal process, so where the tool is a constant temperature, then it can be even quicker. It's a matter of minutes, just 1 or 2 minutes. Otherwise, it's a bit more, but still a lot shorter than an autoclave cycle. Yeah.
Okay, thank you. So the next question from Michael Buck. What is the current status of oven vacuum back consolidation for out-of-autoclave?
Yeah, so oven consolidation has been in use for many years for carbon peak at Daher, for example, in France, making a very elegant floor structure for the A400M, which consists of panels and beams, which are oven consolidated. So that can be done. Our experience has been that if the layup is very complex, with a lot of thickness variation, it's a bit more difficult to just go with vacuum. And also a vacuum process in an oven is not very fast because heat has transferred with only 1 bar pressure or less, because an oven is an atmospheric condition. So so it does exist. But I guess if you want to go into high rates, you do want to go into a system where you can basically push in the energy and take it out quickly with a system. Yeah.
Thank you. So the next question is from David Haber. What is the hydrostatic membrane? Metal?
Yes, it is. Yeah.
Okay. The next question is from Jean-Philippe Canard. Thanks for the presentation, Arnt. In the large part press consolidation process you showed at the end, is there a consolidation step after the flat automated layup, or are you going directly to a forming step from the layup?
Let's see. Consolidation showed at the end. I guess it's the big press to make a fuselage panel, maybe. So is there a consolidation after the flat automated layup, or are you going directly to do a forming step from the layup? So I think preferably, if possible, you lay up flat. If you're looking at fuselage type structure, if it's single curved, you would lay it up flat, then place it into the press and then consolidate. Or if it's a very thick structure, you would do fast fiber placement in a tool or on a tool, basically on a positive tool, and then move this layup into the press for consolidation. So I don't know if that answers the question, but yeah.
Okay. And then again, if you want to continue to have more questions, please feel free to put them in the Q&A. And then also, if needed, I can promote you and you can ask your question if you let me know.
Yeah.
So the next question is from Ryan Hosh. What are the typical pressures used to consolidate a structural composite part, such as a stringer or frame with a continuous fiber thermoplastic material?
Yeah, so typical pressures to create good quality components in continuous fiber reinforced thermoplastic is several times atmospheric. Where atmospheric is 1 bar, it would be several bar. Anywhere between 3 to 6 bar, for example, is fairly typical to give good quality. Yeah.
Okay. And then
I guess if I could jump in as well, on
Sure.
I think fabrication of small to medium-sized parts in thermoplastics is pretty well established, but as you obviously have indicated, the assembly is really a key step and a great opportunity with thermoplastics. I know you've done quite a range of different techniques, different welding methods, co-consolidation. I mean, would you say there's a preferred method from your experience?
To join parts together, you mean?
Yeah, yeah.
Well, not really, because we often see that it depends on the material that you use and the design of the component and the amount of components to be produced. So sometimes ultrasonic welding is ideal, sometimes it's induction, otherwise it can be resistance welding. And then we also have conduction with a hot element. So it's not so straightforward to say we have only one technique, which works best. Yeah.
Okay. All right. Good.
Thank you.
okay, so we have another question from Michael Buck. Are there any advantages or disadvantages for amorphous versus semicrystalline polymers for out-of-autoclave processing?
Yeah, I guess both materials are suited for out-of-autoclave processing. So I guess it's more depends on other factors, such as do we have aggressive solvents in the application, and therefore do we need semicrystalline materials, or can we work with amorphous materials? Yeah.
Yeah. And then we have Ji Su, who raised his hand. His or her hand. I'm just gonna promote.
Yeah.
You. Okay, please go ahead.
The question you asked is my question.
Okay, the question that was just asked now.
Yeah, we got the same idea at the same time. Yeah.
Good.
Yeah.
Okay, good. Okay, so for the next question from Patrick Johnson, what concerns are there for airworthiness certification of welded thermoplastic structural components?
Okay, so yeah, our experience is that we have proposed welding first in 1998 for the wing leading edges of Airbus. This was with the European authorities, the CAA. And then this was about 9 years later for the FAA in the United States on the control surfaces in carbon material. And in both cases, it was important to show the fact that the interface can be reliably joined in a welding process as long as you can guarantee the fact that you have reached pressure and temperature. What we showed, for example, is that there is very little effect of contamination. So we even did tests with grease from your finger, and there was no effect. So that means it's a robust, very robust joining process. And and the authorities have accepted this. I know with bonding, we also want to bond without any bolts, but that's a more difficult discussion with the authorities. But with welding, because you're basically joining two similar or identical materials, that there is no second material being added at the interface, that makes the discussion with the authorities a feasible proposition. Yeah.
Sorry, I was muted. So thank you. For the next question from Deepa Roy, is there any risk of thermo-oxidative degradation during press processing? For example, for peak high processing temperature is needed.
Yeah, so you do have to make sure that the time exposure of the laminate in the press forming process is not exaggerated, so not too long. But if you remember the wing leading edges and also the control surfaces of aircraft, the ribs are stamp formed in a normal environment, so not in an inert gas environment. The flanges are cleaned, and then they are well suited for a welding process. So as long as you respect the process conditions which are developed with a limited exposure at very high temperature, then the interface is fine for welding in a structural manner. Yeah.
Thank you. For the next question from Lina Gambari, between PPS versus PEEK and versus PEC, which material is better suited for high-rate out-of-autoclave thermoplastic composite manufacturing? And are there ideal material properties for fiber/polymers for out-of-autoclave thermoplastic composite manufacturing?
So PPS has slightly lower TG and lower melt temperature than PEEK and PEC. For the rest, it's also a semicrystalline polymer. So I guess both are suited for out-of-autoclave processing. It's just that the properties are slightly different, and also the temperature resistance is a bit more limited with PPS. So it's more a question of what structural category are you developing and which material do you prefer for that. Yeah.
Okay, thank you. So we have the next question from Romain. In the process of joining a rib or a spar to a skin by induction welding, it seems it was done without using a susceptor material. How do you control the heat generation in the carbon fibers to avoid consolidating the parts?
Yeah, so indeed there is no susceptor in between, and a control is done because the parts are pressed against each other with a kind of a bladder. So it's an inflatable bladder, which pushes the rib flange or the spar flange against the skin. So that makes sure everything is compressed, and then the induction equipment moves slowly along the product, and the tooling is non-conductive, so that generates a local melting zone which moves along the joint. And on the outside of the part, on the skin, you have a heat sink which basically absorbs the energy and makes sure it stays cold and doesn't change shape on the outside.
Thank you. And I have a follow-up question with that. What was the speed to conduct that weld?
Yeah, so speed of induction welding is, I guess, roughly about, what is that in inches, maybe 10 to 15 inches a minute, roughly.
Okay.
So that may seem a bit limited, but at the same time, it's a fully automatic process. So in the picture I showed you of the factory facility, it runs at night without anybody present. So the robot does its work without people. So, yeah.
Okay. So the next question is from Sana. How much of a deep draw or minimum size of complex features, bending radius, that you can achieve with compression molding of continuous fibers of these structures?
Yeah, so I showed a picture in the very beginning of a deep drawing part in glass fiber from the early days. It's like a Coca-Cola can, basically. So you clamp your thermoplastic. The fabric has to be very loosely woven, and then you can make an incredible deep drawing movement. So I think there's very little limitation of what you can do depending on the fabric and the weave that you use. It's the same as with dry fiber, basically. Yeah.
Okay, thank you. The next question is from David Hauer. What is your view for using in situ consolidation for the next generation aircraft or UAM?
Yeah, so we are researching in situ consolidation. We are participating in a European clean aviation project, which is after Clean Sky 2, called Herwinged, with Leonardo as a partner. And we have taken up the challenge to work on in situ as well as others have in parallel. But to be honest, there are a lot of challenges with in situ on process speed, on part quality, on thickness control. So it's it's something to be researched. That's the holy grail, as it has been for many years. So yeah, we'll see. Yeah.
I guess let me maybe jump in with one more on the only one that often comes up with thermoplastics is what about repair? What would you say is sort of the state of the art of thermoplastic or repair of thermoplastic composite components?
Yeah, I guess with repair, it's also holy grail that you would want to melt your damage together and to basically use the meltability of the thermoplastic polymer to do repairs. At the same time, when you do that, you have to have some kind of tool to hold your laminate in shape, because it will lose its shape while you do that. So today, repair is still fairly conventional with with thermoset laminating and patch repair, bolting of patches, like at your dentist, filling a hole. But in theory, it would, there is the opportunity to go into real thermoplastic repair by welding. But today we're not yet there. So an invitation for people to work together in this common target. Yeah.
Yeah, I think that's actually a very good point, and maybe something, in terms of organizations like SAMPI as well, that some of these challenges really require the industry to come together. It's not something that one individual player can work on. Yeah,
because it concerns us all, and of course it's maybe not your core business to do repairs, but it's very important for customers to have repairs. Yeah.
And it's something quite multidisciplinary as well.
Yes.
The aspect of repair. So I agree with David that this is something that we should draw expertise from everybody who's involved, actually, who has an interest. And I know there has been quite a bit of an interesting mission on the subject, finding this holy grail. Okay, so we have a question coming up from Alberto. Are any other polymer grades that are well positioned to take advantage of out-of-autoclave processing to expand the range towards either higher or lower temperature requirements than PPS and PEEK?
So there are several polymers being used in combination with fibers, mostly carbon fibers, like Toray, for example, has a low melt PEEK material. So these types of polymers with carbon fibers, mainly as tapes, are being qualified and researched with respect to out-of-autoclave consolidation. Yes. So there's an increasing range of materials that have come up. Yeah.
The next question is from David Hauer. Dual polymer bonding for repair, PEI film.
Yeah, well, I think that's almost more of a comment than a question, actually. But
it did have a question mark, so
okay.
there you go. So I'm reading them out. If they want to come up, I can make you host as well.
Why not? Why not? But maybe depending on the classification of the part. If it's really primary structure, you would want to try to not add another material, maybe on the interface. But yes, you could use multipolymers for repair.
Yeah. I mean, I think one of the points is using both a low temperature material or material that can be processed at low temperature, I should say.
And this has been done before as well. Same in the apogee of the late 80s, early 90s. And this is something personally I'm researching very heavily. On how to perform repairs using particularly PEEK substrates with PEI film.
Okay. Well, thank you very much, Arnt. We're almost at the end of our hour here. Really appreciate you giving us this sort of I guess, sorry, there's one more question.
One last question from Sana. One last question.
Yeah.
So what is your opinion? Oh, there's two coming. What is your opinion on adoption of long fibers discontinuities, of long fiber discontinuous thermoplastics in semi-structural applications?
Yeah, no, it's a very good idea. But if you look at recycling, for example, and basically cutting up either excess production material or end-of-life products, you are creating continuous fiber products with shorter fiber. So let's say discontinuous fiber products. So yes, very good idea. Yeah.
And then one last question. Now for real. Joseph Krena asks, where was the cracking line on your consolidated T profile in the case pull-out tests?
Yeah, so we've done a lot of testing also on large panels, and what we saw is that depending on the geometry, we get cracks in let's say in the skin itself that connects the stringer, and if the skin is bending very strongly, we can get a crack in the radius. So it depends on how you design the part. You have to design it for maximum strength and the right failure mode. Yeah.
Okay, thank you.
All right.
Okay.
Well, thank you again, Arnt. This has been
Yeah, thank you
a
too.
great overview, and I know kind of you and
Thanks
the
for the
GChem,
discussion.
yeah,
Yeah.
GChem Fokker group have done a great amount of work over the years, so we really appreciate you sharing that with us, and especially answering such a wide range of different questions here during the session. So I think again, Arnt was saying for those of you in Europe, he will be at the SAMPI Europe conference coming up soon in Madrid, right, Arnt?
Yes.
And I know you're often at GEC and the Spring SAMPI Europe meeting around that as well. So
Yes.
good opportunities to connect with Arnt in person as well if you want. So thank you again. Really appreciate you joining us today. And
Thank you too.
obviously, if I know I think we have a broader group of people today, so if anyone wants to connect with us, just go to the SAMPI 365 site, and the thermoplastic technical committee is under the groups there. You can connect with us and sign up for the group. So thank you again.
Yeah. Thank you, David, Julieta, and everybody for the good discussion as well. Thank you.
Thank you.
Thanks.
Thank you.
Bye.